Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 19. In this lecture, we'll discuss standing waves. This topic is covered in Chapter 18 of our textbook by Survey and Jowett. Recall that we've been discussing the superposition of waves. Roughly speaking, superposition refers to the combining of two or more waves. So when two sound waves or rope waves or water waves, for example, are present at the same time in the same medium, we describe that as the superposition of two waves. Now, there are many different types of waves and many different ways that they could be combined, so superposition can in general be a very complicated topic. However, we wanted to take a very systematic tour of this topic, so we've been carefully discussing the superposition of two sinusoidal waves that are nearly identical except one or two parameters might be modified. In this lecture, we want to discuss this specific example here. We've briefly discussed this example before, but now we want to discuss it in much more depth. Consider the superposition of two sinusoidal waves of equal amplitude, equal wavelength, equal frequency, and equal phase constant, but propagating in opposite directions. So here is wave 1 and here is wave 2. You can see they're nearly identical except we have a minus sign here indicating that wave 1 is propagating to the right or the positive direction. And we have a plus sign here indicating that wave 2 is propagating to the left or in the negative direction. Combining these two sign functions using this trigonometric identity that you see at the bottom, you get this new function over here. This new function has some interesting properties. Note that the variation with space is encapsulated in this sine function here, but the variation in time is encapsulated in the cosine function here. This entire quantity, 2a cosine omega t, is referred to as the amplitude of the superposition or amplitude of the resultant wave. This particular wave is referred to as a standing wave, and the reason for it is that when you look at this wave, you will see that it doesn't really go anywhere, it simply stays in place. This animation here shows a standing wave. As you can see, we have two counterpropagating waves. The green wave is moving in the positive direction, the blue wave is moving in the negative direction, and the resultant is simply staying in place. There are oscillations. The amplitude of the resultant depends on time. Sometimes it's really big and sometimes it's really small. But as you can see, the energy is not really being carried to the left or to the right. It is simply stored in place. Standing waves have many interesting applications, and the purpose of this lecture is to discuss standing waves in much greater detail. Now, as you've seen, in order to have standing waves, we need two counterpropagating waves. In other words, we need two waves that are identical except that they are propagating or traveling in opposite directions. One way to achieve that is, for example, to have two audio speakers that are facing each other. So one audio speaker is broadcasting sounds to the right, while the other one is broadcasting sound waves to the left. The superposition of these two sound waves can result in standing waves. However, a much more common situation is when a single wave reflects from its boundary conditions. Recall that when we were discussing rope waves, we discussed the boundary conditions of the rope. In other words, we discussed what happens when the wave reaches the end of the rope. Of course, you can avoid that discussion by considering infinitely long waves. However, that's not a very realistic situation. Eventually, the wave will reach an end, and what happens at the end of the rope determines how the wave is reflected. You can have a situation where the right end, for example, as shown in this picture, is fixed in place. So the final atom or element of the rope is not allowed to oscillate. In that case, the energy is reflected from the boundary condition, but the reflection is inverted. It is turned upside down. We sometimes describe that by saying that the phase of the wave changes by pi radians. That's because if you change the phase of a wave by pi radians, if you take a sine function and shift it by pi radians, the wave essentially flips upside down. Of course, you can also have a free end. In other words, the last molecule or last element of the wave is not fixed in place. In fact, it's allowed to move up and down freely. In that case, the energy still reflects from the boundary condition, but it is not inverted. We say that the phase change is 0 radians. It turns out this reflection of the wave is important because once you have a reflection, then in an effect you have two counterpropagating waves. You have the original wave that is moving to the right in this picture, and then you have the reflected wave that is moving to the left. How these two combine to create standing waves is a little bit different depending on whether you have a fixed end or a free end. So we need to consider each one of these boundary conditions carefully and see what kind of a standing wave each produces. One application of standing waves is to musical instruments. If you want to understand what notes or what frequencies a musical instrument plays, you have to understand standing waves. Different musical instruments have different boundary conditions. That means that the reflected wave behaves differently for different musical instruments, and therefore we get different types of standing waves and therefore different frequencies. As two examples, consider the guitar and the clarinet. In the case of the guitar, it's the guitar strings that are oscillating, and both ends of the guitar string are fixed in place. So while the guitar string can oscillate throughout its length, the bottom end and the top end of the guitar string are both firmly fixed in place and therefore cannot move. What that means is that when waves reach one end of the guitar from the other end, for example, and they are reflected, that reflection is going to be inverted, resulting in a very specific type of a standing wave. We'll describe those standing waves in detail in just a few minutes, but the types of standing waves you get with a guitar are going to be very different from a clarinet. In the case of the clarinet, the thing that is oscillating is actually air molecules inside this cylindrical body of the clarinet. And in the case of the clarinet, one end is closed while the other end is open. What that means is that the air molecules inside the cylinder are free to move at one end, but are fixed in place at the other end. So the clarinet has two different boundary conditions. On one end it's fixed and on the other end is free, which means we get a different type of reflections inside the clarinet body and therefore different types of standing waves and ultimately different frequencies. Again, we'll discuss these frequencies in detail, but the important point here is that the boundary conditions of the musical instrument, along with a few other factors like the length of the musical instrument, ultimately determine what kinds of frequencies we can play on that musical instrument. To understand how boundary conditions can affect frequency, we need to first discuss wavelength. It turns out the boundary conditions restrict the set of possible wavelengths along the strings of a guitar or inside the air column of a clarinet, for example. A wave with boundary conditions is allowed to have only certain specific discrete wavelengths. This fact is sometimes referred to as the quantization of wavelengths. To better understand that fact, suppose you have a string that is 3 meters in length and it is fixed at both ends. This is something like a very long guitar string. If you have fixed the string at both ends, then the very first molecule and the very last molecule of the string must always remain in place. What that means is that along this 3 meter length, you could, in theory, create a wave that looks like this wave on the left, but cannot create a wave like the one on the right. Notice that in order to have a wave like the one on the right, the very last molecule of the string needs to be able to move freely so that it could achieve, let's say, a displacement of 1 meter. Notice that the wave on the left and the wave on the right have different wavelengths. What this tells us is that some wavelengths, like the one on the left, are possible, and some other wavelengths, like the one on the right, are not possible. So we need to have a detailed understanding of exactly what wavelengths are possible and what wavelengths are not possible for this particular boundary condition. To understand exactly what frequencies are possible, we need to understand exactly what wavelengths are possible. To do that, we need to carefully and systematically enumerate all the possible wavelengths for all the possible boundary conditions. So let's begin with the node-node boundary condition. In this context, the word node refers to a point that has a displacement of 0. So a node is a point along a wave that cannot move. It's a point that is fixed in place. When we speak of node-node boundary conditions, we're basically talking about a string that is fixed on its left end and its right end. So both ends of the string are considered nodes. We could also be talking about a column of air that is closed at both ends, so the air molecules on the left end and the right end are both fixed in place and therefore are nodes. For that kind of a boundary condition, the longest wavelength possible is the one shown over here. Notice in this particular wave here, the left end is fixed and the right end is fixed, and we have a wavelength that is basically twice as long as the length of the string. So if we say that the string is 3 meters long, we are seeing here basically half of a wave. Therefore, the wavelength of this wave would be 6 meters long. It's also possible to have this kind of a wavelength. This particular wave has nodes on the left end and on the right end, and also one right in the middle. If the length of the string is 3 meters, then the wavelength of this wave is also exactly 3 meters. You can make the wavelength a little bit shorter. For example, you can have this type of a wave. However, as you make the wavelength shorter, you need to make sure that the left end and the right end always coincide with 0 displacement. Remember that we want the left end and the right end to be nodes. Specifically, we want the molecules on those two ends to be fixed in place. You can continue to make the wavelengths shorter in a very systematic and controlled manner, and you would see that the next shorter wavelength possible would correspond to the wave over here. Let's make this discussion more precise by calculating the wavelength for each one of these situations. Generally, we label each one of these modes of oscillation using an integer. So we call this first one n equals 1, n equals 2, n equals 3, and n equals 4. For the n equals 1 mode, you can see the wavelength is 2L. So if the length of the string is L, the wavelength of this particular mode of oscillation for this particular standing wave would be twice the length of the string. For this particular standing wave here, you can see that the wavelength, lambda, is simply equal to L. It's simply equal to the length of the string. Here the wavelength is shorter. As you can see, one wavelength goes all the way to 2 meters. So we can see that the wavelength is 2/3 of the length of the string. In this last case, we can fit 2 complete wavelengths along the length of the string. One wavelength is basically half of the length of the string, so we say lambda is L over 2. As you look at these wavelengths, hopefully you're noticing a pattern here. Our goal is to develop an equation that tells us exactly what the possible wavelengths are for this particular boundary condition. Another possible boundary condition is the node-antinode boundary condition. We've already mentioned that a node corresponds to a point that has 0 displacement, An antinode corresponds to a point that has the maximum displacement. So a node corresponds to a fixed end of a rope, but an antinode corresponds to a free end of the rope. An antinode is a point that basically oscillates through the full range of motion for that particular wave. So when we speak of node-antinode boundary conditions, we're imagining a string that is fixed at one end and free at the other end, or we're imagining a column of air that is open on one end and closed at the other end. What are the possible waves that you could have in this situation? Well, I've enumerated them here in order of decreasing wavelength. With this top standing wave or top mode, what we have is a node on the left side and an antinode on the right side. You can see this is really 1/4 of a wavelength. If you were to complete this wave, it would be 4 times as long as the length of the string. If the string is 3 meters long, we would say that the wavelength of this wave is 12 meters. Here's another possibility. Again, I've fixed the left end, and the right end is going through maximum displacement because it's an antinode. As you can see, in this case, what we have is not a complete wavelength, but 3/4 of a wavelength, which means a wavelength would be 4/3 of the length of this rope. Here's another possibility of a slightly shorter wavelength. Again, we have a node here, and we have an antinode on the right-hand side. If you make the wavelength a little bit shorter, you end up with this standing wave over here. This is simply the next mode. Again, we'd like to have equations for each one of these wavelengths. If you think about these a little bit, you'll see that the wavelength of the first wave can be described as 4 times the length of the rope. In the second case, it could be described as 4/3 the length of the rope. In this third case here, which we're calling the n equals 3 mode, you can see that one wavelength starts from here and ends over here. That's not the full length, but 4/5 of the length of the rope. So we would say the wavelength is 4/5 L. And in this final case, you might have to think about it a little more carefully, but if you divide this stretch of rope into 7 equal pieces, you would see that one wavelength stretches across 4 of those pieces, so the wavelength would be 4/7 L. There is a final possibility for the boundary conditions. One could also have an antinode boundary condition. This is a situation where both ends of the rope are free to oscillate, or a column of air where both ends are free to air, so the air molecules on the left end and on the right end are all free to oscillate. What are the possibilities there? Again, you have to systematically enumerate these. I have listed them here in order of decreasing wavelength. As you can see, this is the very first possibility. This is the longest wave that you could have. The left end is an antinode. It's oscillating. It's going through its maximum displacement. And the right end is also an antinode. As you can see, this is not a full wavelength. This is really 1/2 of a wavelength. So if I asked you what's the wavelength of this mode here, you would say it's twice the length of the rope. So if the rope is 3 meters long, we would need to have 6 meters of rope to see the entire wavelength. In this case here, notice we have a complete cycle. We have a complete wavelength along the length of the rope. So we would say that the wavelength is equal to the length of the rope. I have enumerated the next 2 shorter wavelengths here. And if you were to actually calculate the wavelength, you would see that the wavelength for the first one is twice the length of the rope. The wavelength for the second mode is simply equal to the length of the rope. For the third case, it's 2/3 the length of the rope. And then finally, it's 1/2 the length of the rope. Notice how the node-node boundary condition is similar to the antinode boundary condition. The shapes of the waves are certainly different in this first column and in this last column. However, the wavelengths are the same. As I said, our goal is to have a formula that describes all of these possible wavelengths in a rather systematic manner. These are the three formulas that we'll need for the three different boundary conditions that we're going to encounter. When we have node-node boundary conditions, so that's like a guitar string, something that's fixed and fixed on both ends, then we find that only certain wavelengths are allowed. We label those using the integer n. The longest one is referred to as the first mode, and then the second mode, and the third mode, and in general we could have the nth mode. For the nth mode, the wavelength is going to be 2L over n. So twice the length of the rope divided by the mode that you're interested in. If you want to know what the 17th shortest wavelength is, you would multiply the length of the rope by 2 and then divide by 17. If you look at the pattern here, you'll see that the node-antinode boundary condition has a slightly more complicated formula. It's always 4 times the length of the string or the rope divided by odd numbers. Notice we have 4L divided by 1, 4L divided by 3, 4L divided by 5, and you can generate the odd numbers by taking the integers, multiplying by 2, and then subtracting 1. So n is simply the integers, 1, 2, 3, 4, 5, so on. When you multiply the integers by 2, you get the even integers, and then when you subtract 1, you get the odd integers. So when you have a musical instrument that is fixed on one end and free on the other end, the possible wavelengths are given by this formula. Take 4 times the length of the musical instrument and divide it by an odd number. If you want to know what the 5th mode of that musical instrument is, you would take 4L and divide it by 9. So 2 times 5 minus 1. If you have antinode boundary conditions, the wavelengths are identical to those of the node-node boundary conditions. So although the waves themselves look different, the wavelengths are the same. They are given by the same formula, 2L divided by n, where, as always, n is an integer, 1, 2, 3, 4, 5, and so on. So we can summarize the discussion so far as follows. The different boundary conditions on waves affect how waves are reflected. How waves are reflected affects the types of standing waves that we could have. Specifically, it affects the types of wavelengths that we could have. If we have node-node boundary conditions, for example, a string that is fixed at both ends, then the only possible wavelengths that are allowed, given that both ends must be fixed, are given by this formula here. If you have a string that is fixed at one end and free on the other end, we describe that as a node-antinode boundary condition, then the only possible wavelengths are these ones. There are infinitely many possible wavelengths. However, you can't have just any wavelength. The particular wavelengths that are allowed are provided by this equation here, where n takes the values 1, 2, 3, all the way to infinity. Finally, for the antinode boundary condition, the possible wavelengths are given by this equation here. The allowed wavelengths that we were just discussing for the different boundary conditions are ultimately related to the concept of resonance. Recall that we've discussed resonance before in the context of simple harmonic motion, when we were talking about the motion of driven oscillators like a pendulum or a mass spring system. We found that these systems have certain preferred frequencies at which their amplitudes are maximized. For example, if you are pushing a friend on a playground swing set, there is a special frequency at which you can push her in order to maximize the amplitude of her motion. For a mass spring system, the amplitude is given by this complicated formula. you can see that the amplitude is a function of omega sub d. Omega sub d is the angular frequency of the driving force. You can maximize this function if you set omega sub d equal to this particular expression here. This is the frequency that maximizes the amplitude of the oscillations. In some sense, this is the favorite angular frequency of the mass spring system. We refer to this favored angular frequency as the resonance angular frequency. The resonance angular frequency is the frequency at which the mass spring system has its largest amplitude and also greatest amount of energy. We can apply the same concepts to waves. For a mass spring system, there's only a single mass that is oscillating. However, for waves, there are many masses that are oscillating. Each individual atom or molecule of a stretch of rope is oscillating simultaneously. So a wave has many resonance frequencies, and we can ask, what are these resonance frequencies for a particular wave? It turns out these resonance frequencies correspond to the allowed wavelengths that we just calculated. A little more precisely, we could talk about the resonance frequencies or optimum frequencies for creating sound on a string of length L that is fixed at both ends. In this case, those optimal frequencies or resonance frequencies for the node-node boundary condition would be given by this formula here. N, as usual, is the positive integers, 1, 2, 3, and so on. V is the speed of the sound waves, and L is the length of the string. Notice that this formula essentially comes from formulas that you've already seen before. You've already seen that for node-node boundary conditions, the allowed wavelengths are 2L over N. You've also seen that wave speed for any kind of a wave is equal to frequency times wavelength. So rearranging this formula, we find that frequency must be equal to V over lambda. And if lambda is 2L over N, substituting that expression in here, we find that frequency must be NV over 2L. So these are the resonance frequencies of this particular string. These are the frequencies at which the particular string has the maximum amount of energy and the largest amplitude. We could ask the same question for a different type of string, one that is open at one end and closed at the other. Here we're talking about node-antinode boundary conditions. And the formula is slightly different. Now we find that the resonance frequencies, those frequencies that have the most amount of energy, are given by this formula. Once again, we're taking V, which is the wave speed, and dividing it by the allowed wavelengths that we carefully found a couple of slides ago. These special or optimal frequencies are sometimes referred to as harmonics in the context of musical instruments. So musicians often talk about the first harmonic or the second harmonic or the third harmonic. They're basically talking about the frequencies that correspond to n equals 1, 2, 3, and so on. Let's end this lecture with a practice problem. Consider a guitar string with a length of 64 centimeters and a mass of 3 grams at a tension of 150 newtons. Roughly speaking, these are typical numbers for a typical guitar string. Calculate the frequencies of the first 3 harmonics of this particular guitar string. So we have a string and we have some specifications for it, like its length and its mass. And if we were playing this guitar string without fingering it or using the frets, so simply plucking the guitar string like any amateur guitar player can, what would be the frequencies that this guitar string can sustain? What are the resonant frequencies? These are the harmonics of this particular string. In particular, we're interested in the first 3 harmonics. So we're talking about the n equals 1, n equals 2, and n equals 3. Now recall that we have a formula for the harmonic or resonant frequencies. The formula was this. We know the length of the guitar string L, that's given to us as 64 centimeters. We probably want to convert that to meters. However, we don't know the speed of the sound waves along these guitar strings. Recall that we know for rope waves, the wave speed is equal to the square root of tension divided by the length mass density. The tension is given to us. These strings are each pulled taut by these tuning screws at the top of the guitar. So each one has a certain tension, and in this case, we know the tension is 150 newtons. So if we can figure out the mass density, the length mass density of the guitar string, we should be able to calculate V. And if we calculate V, then we should be able to calculate the frequencies. The mass length density can be calculated by taking the mass and dividing it by the length. Recall that here we're talking about the length density and not volume density. Of course, you should do some conversions. The 3 grams should be converted to kilograms, and the centimeters should be converted to meters. But after those conversions, you should find that the wave speed along this particular guitar string is approximately 178 meters per second. We can also calculate the allowed wavelengths, although this is not absolutely necessary. Recall that for a node-node boundary condition, like a guitar string that's fixed at both ends, the allowed wavelengths are provided by this formula. We're going to use n equals 1, and then n equals 2, and n equals 3. Those are the first 3 resonant wavelengths or harmonics. We find that these are the wavelengths that are allowed, and the frequencies that correspond to these wavelengths can also be found by either taking the wave speed and dividing it by the wavelength, or simply using this formula, which we saw on the previous slide. Doing that, we find that the first 3 resonant frequencies of this guitar string are approximately 139 Hertz, 279 Hertz, and 419 Hertz. There are other resonant frequencies. If you just pluck this guitar string without using any of the tricks that a skilled guitar player would use, you would get many different frequencies, and of all those frequencies, the loudest would be the first resonant one, the next loudest would be 279, and the next loudest would be 419, and the subsequent resonant frequencies would gradually get quieter. The very first one is known as the first harmonic. Musicians often describe the first harmonic as the fundamental for that particular musical instrument. Let's continue with the same practice problem. It turns out that the guitar string we described on the previous slide was slightly out of tune. Musicians can tune their musical instrument using these tuning screws that are found at the head of the guitar. Turning these screws can actually pull the guitar strings, increasing the tension, thereby changing the wavelengths and the frequencies that can be played. Suppose the musician playing this guitar wishes to play the frequency 440 Hertz as the 4th harmonic. The frequency 440 Hertz is often described as middle A by musicians. In tuning the string, what tension should he apply to the string? So he's going to turn one of these tuning screws and either increase or decrease the tension. It was at 150 newtons, and he wants to do this so that the 4th harmonic, that would be n equals 4 frequency, is equal to 440 Hertz. So the goal here is to have F4 to be equal to 440 Hertz. Remember that the nth frequency is n times V divided by 2L. So what we have here is a situation where 4 times the wave speed divided by 2L is equal to 440 Hertz. We know what the length of the string guitar is. That's 64 centimeters. That's not something the musician can change. Of course, he can go and buy a whole new guitar, one that's a little bit longer or shorter, but given that we must use this particular guitar here, the length of the string is going to be fixed at 64 centimeters. What that means is that in order to achieve a frequency of 440 hertz, we need to have a wave speed of 140.8 meters per second. Now recall that the wave speed is related to tension, so now we can solve for tension. Rearranging the wave speed equation, we find that tension is equal to mu v squared. We know what mu is, it's simply the mass divided by length, and v, we have just found that. Substituting that number into this equation here, we find that the tension should be 92.928 newtons. So the original tension was in some sense too high. The tuning screw needs to be loosened a little bit to reduce the tension in that particular string. And that is the end of this lecture. Thank you for your attention.